Good day. So this is design practice 2. Again, it's an exercise that we would normally do in class, and I would be there and I would walk around and we will be doing this exercise. But because I'm not there, I'm doing another video just to guide you through in the beginning. So this here is your design practice, and you have your different tasks just as before. Um, in this exercise, normally what is done, the groups are given, each are given three cross sections, three aluminum members of different cross sections. They're all rectangular solid sections with different dimensions. And they're given measurement instruments and are asked to measure the specimen at 3 points and find the average so that you could get the width and the height of the specimen. Right? They're all aluminum. Right? So first thing you do is you go online and you find the MatWeb website, you find the material properties for aluminum, be it the sigma yield and the ultimate tensile strength. Right, so with the task now, we're using Excel for this exercise. And just as you would have seen in design exercise 2, where a lot of the formulas and the calculation were done in Excel, the same thing we're going to do here. So you're going to open your Excel sheet, right? And I'm going to switch over, you could follow along in your script. Right, so you're going to open an Excel sheet and you're going to create these columns, as seen here. Right, shear force, bending moment, axial force, the dimensions B and D of the cross section. Right, so each group will be given a different bunch of dimensions. Right, and then you enter your formulas for your cross-sectional area, I, Y, tau xy, sigma xl. So you put in these formulas based on what we have done so far in the course and from strengths and from the design exercises to and some of the examples. So we have all this information already. As you could see here for tau max megapascals, what I've done, I've just simply divided it tau max by 1,000,000 to get to the megapascals, right? So when you enter all these formulas, you want to validate the formulas, right? So you would see on the actual script for the design practice, I've actually included the in Excel. So you could see, you could actually test your sheet and make sure that you're getting the correct values. So you put in the values in the green here, which is your inputs, shear force, bending moment, axial, and your dimensions B and D, and just make sure that the sheet is actually doing the proper calculation. So once you have that, then you can move on to the task number 4. And task number 4 is where you obtain your cross-sectional properties. Right, so if we were to look at your group results, so for example, this is group results for group 1, specimen 1. This is the dimensions for B and D, that's a width by height. And you normally would have taken measurements at 3 points along the length of the specimen. Right, so these are the dimensions. And of course, what you do, you find your average and you come down with one value of B, one value of D. Specimen 2, specimen 3 is really specimen 2, but we flip B and D. So we have a cross section that is oriented one direction and we take it and we orient it the other direction. Okay. Okay, so using those values now we could plug in now B and D into Excel, right? And task 5 is using the Excel sheet determine the maximum allowable static bending moment in pure bending. Pure bending means that, right, so in the Excel sheet you're saying that your shear force is 0. So you make your shear force 0, we have your pure bending. Again, pure bending meaning that it is subjected to just a pure bending moment, so we have no axial force. So you make that also equal to 0. You put in your values for B and D, whatever it is, right? These are just different values here. And then you could see now your Excel should actually do the calculation and determine your tau max. If it is, you have enter your formulas correct before, and we said that there's a way to validate that. Right, so if it is your values are looking like this and you want to express it in a way, you could come up here and click that to just on general or number, for example, so you could get it to be 23.09 megapascals, right? So when task 5 asks, it asks to determine the maximum allowable static bending moment that can be applied to its cross section, right? So just going back, over here you should put in a column, right? And call it design, for example, design shear stress. Right, so based on your material properties, what is our design stress? So that is what you have gotten from MATLAB, right? And you're using the tau max, so therefore is maximum shear stress theory. So it is what? Sigma yield on 2n, right? We know that n is 1, that because that said in the script that your factor of safety is 1. So what you're doing, if it is your tau, design shear stress is, say, 30 megapascals. You will be varying m until you could get the 23 to match the 30. Right, so the bending moment right now is 131 Newton meter and the stress is 23, so we could probably increase this 135. Okay, so we need a bigger jump, 150. We go up again, 170. So you see we almost have it. Right, so we could tune it down, so there's no need to really do this fine tuning, but right, well, perfect. Right, so 170.2 Newton meter, we saying therefore is the maximum pure bending moment in a static sense that this particular cross section could handle, given a factor of safety of 1. Alright, so this is how the design process works when we have an open-ended problem, meaning that we have the design stress, and in this case, we solving for m. Right, and we have then a question where we solve for, remember we had solved for diameter in one of the examples. We had solved for maximum force in one of the examples. Right, so in this case, we are solving for 1, but let's just say, for example, we have a shear force. Right, so the shear force is 200 newtons. So you can see it goes up a little. Let's just say we have an axial force of 100 newtons. It goes up. Right, so the Excel sheet allows you to manipulate these 3 values. Right, and you can also see for yourself how little impact the shear force and the axial force has as compared to your bending moment. Right, so that's why. Right, in task 6, they ask now to create another sheet. So you go at the bottom and you add sheet, or you go to sheet 2, and you create again another table. This time you're adding all these different, as you see in the diagram here, all these different headings. Right, and then now you enter your equations for these particular things. So all these equations are in the notes. Right, what might be different is that the n here we have something called the Goodman equation, left hand side, right hand side, and I'll talk about that just now. Sn prime, we did it in the notes as being a half multiplied by sigma ultimate, and that was for steels, but we dealing with aluminum here, so an average value for aluminum is about 0.3 multiplied by sigma ultimate as opposed to 0.5. Right, so this would be the equation for your Sn prime. The Excel, we are here now. This is what we included, and what we did, we included all the equations that were given in the notes. Right, so these are your inputs. B, D, simultaneous is the input. So let's highlight the inputs, and I'll just put a shade on it here so you know what are inputs. So as an input, 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 right, so what is shaded green here are your inputs, right? Where Sn prime, we say it was 1/3 by a sigma ultimate. You could actually even use these values here for CL, CS, CG if you want. Right? The SN, again, formula given in the notes, well, the area, I, Y. And remember your sigma max. The sigma max for pure bending will be what? The My on I, right? As your bending stress, right? M being your M max, min being your M min. Then your sigma mean calculation, your sigma alternating calculation, and then the left hand side, right hand side. So this was the Goodman equation. We have the left hand side, that's this here, and then we calculate the right hand side, which is this here. And in order to balance it, remember in the notes what we did, we had an unknown, and we had solved for the maximum allowable force. Right, that was the first example. Right, so the variant plus or minus P that will allow us to have infinite life. Right. Um, in this case here, we want to find a plus or minus M, the actual thing here. After you input your values again, just like before, you test the worksheet to make sure it's giving you the correct values. Right, so you could input these values here, just as I highlighted green just now in the Excel, and see what calculations you are getting and ensure that you're getting the same values here. Right, so now task 9, using the sheet, determine the maximum allowable reverse bending moment that can be applied to each section. Assume a safety factor of 1. Again, just like before, we're looking at a plus or minus M. So we had max and we had M min. M max and M min. Right? Now, we had plus or minus M, meaning that whatever M max is, M min is the same value but negative. So what we could do, we could say let this here equal to negative 1 multiplied by that value, such that it would one be plus and one be minus. And in this case here, what we could do, we could fluctuate. Right? So the name of the game here is to try and to get the left hand side equal to right hand side. We know our right hand side is 1 on n, which is 1, and we want our calculation here, which is the left hand side, to be equal to 1. Right? So in order to get that plus or minus m that can be applied, we fluctuate this. So we see it's already crossed there 1.13, so we could bring this down 205, for example, 200, 190. Right, so again, you fine tune just like we did before in this case here. Right, so whatever these values were, this were 6 millimeters by 51 millimeters. That was this particular dimension. So in this case, the maximum allowable reverse bending moment in this case is 185 newtons. Right, so for both tasks, 1 and 2, you're doing that for all 3 specimens. Right, so you could recall in your data sheet, you have 3 tables for 3 particular piece material. You could just, what you could do, drag this down like that. So you're putting your specimen 2 here, B and D, specimen 3, B and D. And the same you could do for your fatigue. So you do it for the first one, and then you're doing the next one, you balance again, you do the third one, balance again. Right? Right, so number 10, obtain the permissible bending moment to weight ratio per length for each section for both static and fatigue loading. So basically what you're doing is that you're getting something like a strength to weight ratio kind of thing, right? The permissible load to weight ratio. Right, so it's per unit length. So what you could do is use the density of the aluminum, get the mass per unit length, and when you obtain the mass per unit length, then of course you have the bending moment. You could divide the bending moment by the mass per unit length, and that will give you a ratio for both static and the fatigue case. Alright, so do that also within the Excel sheet. You could use Excel to do the calculation. Alright, and number 11, what other design constraint in addition to maximal allowable bending moment can be utilized in selecting appropriate aluminum cross section? Well, you discuss this with your group members, and what you do, you write the answer right in Excel. So you could just come right here and type out the answer if you want, or answers if you want, right? So all they're submitting is your X, right? So your submission will be this Excel sheet. Right? You submit the Excel sheet identifying for bending moments, the task 9, and right. So this, once you have it labeled properly and then like how I have it in the Excel, then that's fine. Right, the bending moment to weight ratios, you could probably create another column on the end showing these ratios for each specimen, and then your answer to number 11. Right, so if you have any questions, remember you will have 1 week to do this from when it's uploaded. So make sure and work with your group and feel free to ask me any questions on Canvas.